Welcome to this channel. In this video, we will see complementary sets with property and De Morgan's laws. The set theoretic difference of two sets A and B is the set of all elements in A that aren't in B. It's usually denoted by a backslash and can be thought of as like subtracting B from A. I'll call it A minus B for the rest of the video, but remember, this is just to make things easier to say. For example, if A equals the set containing 1, 2, 3, 4, and 5, and B is the set containing 2, 4, 6, and 8, then A minus B is the set containing 1, 3, and 5, since we've removed the 2 and the 4 that were in B. BA is 6 and 8, since we've again removed 2 and 4. If B is a subset of A, the set theoretic difference of A and B is called the complement of B with respect to A. It's usually denoted with a superscript C above the subset B, or as C with B in brackets, like a function. Why is this important enough to give it its own name? Well, it's kind of like a background to B, the things outside of B. In general, it's elements not in the set we're interested in, but not totally irrelevant. Here is where we introduce the universal set. The universal set U is a set of all elements that are relevant for some given topic of interest. If our set A isn't the subset of something specific, we usually assume the complement to A is the universal set. And what that universal set is depends on context. This quote from the Foundations of Mathematics by Stewart and Tall sums it up nicely in a discussion about dogs. When thinking about all non-sheep dogs, it's pointless to worry about camels. Imagine we're throwing two dice. Let A be the number of outcomes of rolling a pair of dice in which both dice show the same number. A sensible universal set in this case would be the set of all possible outcomes of rolling two dice, and the complement of A would be the outcomes where each die shows a different number.
Here's some other examples of complements. The complement of the set of odd numbers is the even numbers, and the complement of the rational numbers is the set of irrational numbers. Notice, with the complement, we often get something that feels like the opposite of the original set, and that's because the complement negates the predicate. With our set builder notation, we have a set A, which contains all X from some set B, such that it fulfills some predicate P. Well, the complement of A, the things not in A, must by definition not satisfy P. So the complement of A is the elements X in B such that P isn't true. And we have this symbol before P to say it's not true. For example, if A is the set of animals that are dogs, then the complement of A is animals that aren't dogs. Let A and B be subsets of the universal set U. Because nothing is in the empty set, its complement is U. Similarly, the complement of U, which contains everything, is the empty set. Here's an interesting one. The complement of a set returns the original set. That's because taking the complement of A leaves all the things in U, but not in A. Taking the complement again, we can see that all that's left in U, but not in our current set, is A. If A is a subset of B, then the complement of B is a subset of the complement of A. It's easy to show visually why this is true, since everything in A is also in B. There are things in B that aren't in A. I'm assuming that they're not equal here. That means that these elements that are in B but not in A will turn up in the complement of A but not the complement of B. And so we end up with the complement of A containing everything in the complement of B and more. We now have the famous De Morgan's laws. First, the complement of A union B is A complement intersect B complement. And second, the complement of A intersect B is A complement union B complement.
Let me show you some examples so you can see what's going on here. Let U be the set of all animals, and let A be the set of dogs, and B be the set of cats. The De Morgan's laws say that the complement of dogs union cats is equal to dogs complement intersect cats complement. Animals that are neither dogs nor cats are not dogs and are not cats. You can see that this makes sense logically. To illustrate the second law, if U is the set of natural numbers, let A be the set of prime numbers and B be the set of X in the natural numbers such that X is less than 100. Using the De Morgan's law, we get that the complement of prime and less than 100 is equal to the complement of prime or the complement of less than 100. Remember, the complement is like changing true to not true, and so we get the set of numbers that are not prime and less than 100 is the set of numbers that are either not prime or greater than 100. Notice that we're allowing numbers greater than 100, but only those that are not prime. We've had a few examples so far of identities which still work when we switch the intersections and unions. This is a general rule that always works and is called the De Morgan duality principle. Given any set theoretic identity involving the union and the intersection, if the union and intersection are interchanged throughout, then the result will be another valid identity. So for all of these identities you've seen so far, that they come in pairs, you'll be happy to know that you can just remember one of them and exchange the union and the intersections to get a second one. The elements of a set may be sets themselves. If we have this set A, then the set containing 0 is an element of A, but not 0 on its own. Since the elements of A are all sets here, it becomes tricky to keep track of what's an element and what's a subset. The set containing 0 isn't a subset of A. It's an element, as we've seen already. In fact, the set containing 0 is a subset of A. And it's important to really think about the difference in cases like this. The power set is a common thing to encounter, and it contains all subsets of a given set. So let A be a set. The power set of A contains all sets X such that X is a subset of A. So for A equals the set containing 0 and 1, the power set of A would contain the empty set, A itself, the set containing 0, and the set containing 1. We also have what are called index families of sets. Essentially, each element, which is a set itself, is indexed by a number and usually written as a subscript. So A, being an A sub I family for I in the set 1, 2, 3, is saying that A contains 3 sets, A1, A2, and A3. And in some cases, it might be easier to read if we package things up like this. If A is a set containing set 0 and 1, and set 0, 1, and 2, we can write this as A1, A2, and A3, where A1 is a set containing 0, A2 is a set containing 0 and 1, and A3 is a set containing 0, 1, and 2. Imagine a set containing everything in the universe, everything you can imagine, all the combined knowledge of everyone on Earth, and more. We'll call this set omega. Because omega contains everything and it itself is something, then we have this interesting property that omega contains itself. This leads to a kind of infinite regress of omegas within omegas. To avoid this, we might change the definition of omega and let omega be the set containing all sets that do not contain themselves. Now assume omega isn't a member of itself by definition, then it must contain itself. If it does contain itself, well, it can't contain itself. This is known as Russell's paradox. In fact, this is less a problem with how we've built the set and more a problem of how we define what a set is in the first place. Naive set theory in general does not give any guidance on what constitutes a set. Mostly, we don't need to worry about this, but as you've seen, it can lead to problems. Axiomatic set theory aims to navigate the paradoxes of naive set theory by providing a rigorous definition of what a set is in the form of a list of axioms. A statement something must satisfy in order to be a set. Thanks for watching. I'll see you next time.